Hello there. In today's lecture, I'll present the elliptic curve digital signature algorithm, ECDSA. ECDSA was standardized by NIST in the year 2000, and along with the signature scheme EDDSA, is widely used in practice. ECDSA has some domain parameters. These are fixed and common to all users of a system. The domain parameters include the equation of an elliptic curve E defined over a finite field of integers modulo p. For concreteness, let's use the elliptic curve P256. The domain parameters also include the number n of points on the curve, where n is prime. A generator point P on the elliptic curve. This can be any point except the point at infinity. And a collision-resistant hash function h. For the sake of concreteness, we'll take it to be SHA-256. Like all signature schemes, ECDSA has three components: key generation, signature generation, and signature verification. In key generation, each user Alice does the following. Alice selects a random integer a between 1 and n-1 and computes the point capital A, which is little a times p. Alice's public key is the point A, whereas her private key is the integer a. Note that computing the private key from the public key is precisely an instance of the ECDLP. And so, if the elliptic curve is chosen such that the ECDLP is intractable for that curve, then no one can compute Alice's private key from her public key. Here is the ECDSA signature generation procedure. To sign a message M of any bit length, Alice uses her private key A as follows. Alice computes the hash M of the message capital M and interprets the hash value as an integer. She then selects the per message secret K, which is a number selected uniformly at random between 1 and n-1. Alice computes the point R, which is k times p, and lets R be the x-coordinate of the point R modulo n. She checks that R is non-zero. If R is 0, which happens with negligible probability, then Alice goes to step 2 and selects a new per-message secret k. Alice then computes S, which is k inverse times m plus AR modulo n, and checks that S is non-zero. If S is 0, which occurs with negligible probability, then Alice goes to step 2 and selects a new per-message secret k. Note that k inverse mod n exists because k is non-zero and n is prime, and so k and n are relatively prime. Thus, Alice can compute k inverse mod n using the extended Euclidean algorithm. Alice's signature on the message M is the pair of integers R and S. Hence, an ECDSA signature is comprised of two integers between 1 and n-1. The reason that R should be non-zero is because in the generation of S, the private key A is multiplied by little r. If R were 0, then the private key A would not be used in signature generation. The reason that S is non-zero is because we need to find inverses of S modulo n in signature verification. The per-message secret K should be securely deleted after it has been used. Suppose that the adversary learns a signed message that Alice generated. Suppose also that the adversary can learn the per-message secret K used to generate that signature. From the signature equation, we can see that the only value that is unknown to the adversary is little a. And so the adversary can efficiently compute Alice's private key A. Thus, per-message secrets must be securely generated and securely deleted. It's also important to note that a fresh random K should be selected each time Alice signs a message. Suppose that Alice signs two messages, M1 and M2, using the same per message secret K. Suppose also that the adversary learns the messages M1 and M2, and also their signatures RS1 and RS2. Notice that the signatures have the same first component because Alice used the same per message secret K to sign both messages, and K determines R. Looking now at the signature equations, we see that the only unknowns to the adversary are K and A. So these two signatures give the adversary two linear equations in the two unknowns K and A. The adversary can then efficiently solve these two linear equations to learn K and Alice's private key a. This shows that Alice should never reuse a per message secret to sign two or more messages.
However, that's easier said than done. Many ECDSA implementations have been compromised because of the improper generation of per message secrets. One prominent failure is the Sony PlayStation implementation of ECDSA.
PlayStation units are usually sold at a loss. Sony profits by selling PlayStation games. To prevent games and other software that have not been approved by Sony from running on PlayStations, Sony would sign each approved game using ECDSA. Here, M is the code for the game, and RS is Sony's ECDSA signature using its private key a. When a user wishes to play the game, he inserts the cartridge or CD into the PlayStation. The PlayStation then verifies the signature on M using Sony's ECDSA public key A, which is embedded in a piece of firmware on the PlayStation. If the signature is valid, then the game begins. Otherwise, the software is rejected. In 2011, it was discovered that Sony had used the same per message secret key to sign multiple games. This was evident because the ECDSA signatures on the two games had the same R component. So, two such signed messages were used to determine Sony's ECDSA private key a. The private key was published, after which anyone could sign a piece of software and execute it on their PlayStation.
There wasn't much Sony could do about the catastrophic failure, since the ECDSA public key was embedded in firmware on the PlayStations. Also, Sony couldn't easily change its ECDSA key pairs, since games that were already sold would no longer have valid signatures.
ECDSA is a randomized signature scheme. Alice generates a new per message secret key K every time she signs a message M. In fact, if Alice signs the same message M twice, then with very high probability, she'll use different per message secrets K for each signature. And so the two signatures on M will most likely be different. ECDSA can be made deterministic as follows. Alice has a second long-term secret key B, which is a randomly selected bit string of length, say 256 bits. To sign a message M, Alice hashes the concatenation of B and M to get the per message secret key K. Notice that Alice's signature on the particular message M is now unique, since the same K will be used each time she signs the message M. Here is the ECDSA signature verification procedure. To verify Alice's signature RS on the message M, Bob does the following. Bob first obtains an authentic copy of Alice's public key A. He checks that R and S are integers between 1 and n-1. If not, he rejects the signature. Bob then hashes the message. He now needs to check that S was correctly generated using this equation. However, Bob cannot check this equation directly because he knows neither the per message secret K nor Alice's private key A. Let me show you how Bob can verify this equation without knowledge of K and A. I'll first interchange S and K to get this equivalent congruence and rearrange terms. Let me define S inverse times M to be U1 and S inverse times R to be U2. And so we get this equivalent congruence. Recall now that the multiples of the point P can be thought of as being arranged around a cycle of length n. And so, since K is congruent to U1 plus U2A modulo n, Kp is equal to U1 plus U2A times P. So we've replaced the congruence of integers with an equivalent equation of points. We'll next replace AP by capital A, Alice's public key, and Kp by capital R to obtain this equivalent equation involving elliptic curve points. I'll next define U1P plus U2A to be capital V. Now, note that if R equals V, then their x-coordinates are equal, and so their x-coordinates modulo n are also equal. The converse statements are false in general, but not by much. Lastly, I'll denote the x-coordinate of the point capital V modulo n by little v. So this explains how the remainder of signature verification works. Bob will verify that S was correctly generated by checking that R equals V. So here's what Bob does. Bob computes U1 by multiplying the hash value little m and S inverse modulo n, and U2 as R times S inverse modulo n. Note that S inverse mod n exists because S is non-zero. Bob then computes the point capital V as U1P plus U2A and verifies that the point V is not the point at infinity. If it is, then Bob rejects the signature. Finally, Bob computes little v as the x-coordinate of capital V modulo n. And he accepts the signed message if and only if V equals R. So we've justified that if Alice properly generated the signed message, then Bob will certainly accept it. ECDSA is believed to be secure, so existentially unforgeable against chosen message attacks, assuming that the ECDLP is intractable and H is a secure hash function. The intractability of ECDLP is a necessary condition because if the ECDLP were easy, then the adversary could compute Alice's private key from her public key. The security claim can be formalized and even proven under some strong assumptions, but I won't do that in this course. Let me next compare ECDSA with the RSA full domain hash signature scheme. For a fair comparison, I'll select parameters for RSA and ECDSA that provide the same level of security, namely 128 bits. So for RSA, we'll use a 3072-bit modulus n for adequate protection against the number-fill sieve factoring algorithm. And for ECDSA, I'll use a 256-bit modulus p for adequate protection against Pollard's algorithm. Now in practice, RSA is generally used with small encryption exponent. For example, E equals 3, or E equals 2 to the 16 plus 1. And hence, RSA signature verification is generally much faster than ECDSA signature verification. This is because the dominant operation in RSA signature verification is the computation of S to the power E modulo n. If E equals 3, then this operation needs only 2 modular multiplications. On the other hand, ECDSA signature verification needs 2 point multiplications, and hence, even though RSA parameters are larger than ECDSA parameters, RSA signature verification is faster than ECDSA signature verification. On the other hand, RSA signature generation is generally slower than ECDSA signature generation. This is because RSA signature generation requires a modular exponentiation, where now the decryption exponent D is full length, namely 3072 bits. On the other hand, ECDSA signature generation needs only one point multiplication. Finally, I'll note that RSA signatures are 3072 bits in length, which are longer than ECDSA signatures, which are 512 bits long. Here are some speed benchmarks from a 2018 implementation of ECDSA with P256 and RSA with a 2048-bit modulus n and encryption exponent e equals 2 to the 16 plus 1. As you can see, RSA is faster than ECDSA for signature verification, but slower for signature generation. Taking these speed comparisons into account, and also the smaller parameters for ECC, and the provision of forward secrecy with ECDH, ECC is generally considered to be superior to RSA. And this is why most new applications in the past few years have been adopting ECC instead of RSA.
All right, so we have come to the end of the Crypto 101 course on cryptographic building blocks. I hope that you have enjoyed this introduction to the wonderful world of cryptography. In this course, we've just scratched the surface. The field of cryptography offers countless and fascinating primitives and protocols that address a wide variety of real-world security and privacy problems. In the coming months and years, we hope to offer more short courses on cryptography and related areas, beginning with the second part of this Crypto 101 course on cryptographic deployments. You can read about our plans for future course offerings on our website, cryptography101.ca. I hope to see you all again in the not-too-distant future.